Welcome to today's webinar presented by FEKO. Application Engineer Peter Futo will be talking to you about EM field considerations in the healthcare industry. Peter joined EMSS in October 2012 and has a wealth of experience in a range of applications, and we're sure you will enjoy the webinar he has put together for you today. Remember that a recording will be available within 24 hours and you will receive a notification email providing a link to view. We encourage you to post questions throughout the presentation for Peter in the area provided on the right-hand side of the screen. The questions will be queued and answered by Peter at the end of the session if time allows. For further information on FEKO, please visit our website or contact your local distributor. You're also welcome to contact us via the email address that appears at the end of the presentation with any additional questions you may have, webinars@emss.co.za. We'd also appreciate you taking a couple of minutes at the end of the presentation to complete our short survey. And to make our webinar more interactive, we'll be launching a couple of polls during the presentation, which we will ask you to please participate in. And on that note, we'll launch the first question. Here we go. Okay, the first question. Do you require phantom or anatomical models for your simulation work? You can answer A, B, C, or D. Please vote now. Okay, that's great. I think we've basically got everybody there. Thanks for participating. I'll now hand over to Peter for his presentation. Hold on a second.
Thank you very much, Fiona, and I'd like to welcome everyone to my presentation today. I think it's fair to say that there is a fascinating technical revolution underway at the moment in the healthcare industry. And what is particularly interesting is that electromagnetics and specifically wireless technologies seem to be playing a key role in many of the developments in this industry. And some of the technologies where this is so affluent is things like remote patient monitoring, vital sign sensors, drug delivery, or active implants like pacemakers or neurostimulators, obviously diagnostic imaging, hypothermia treatment for cancer, or technologies like transcranial magnetics tools. Electromagnetics is used. Now, all of these technologies, when combined with electromagnetics, introduce a whole range of fascinating challenges. Some of these are less intuitive, like the ergonomics that may be involved to develop non-intrusive devices that are comfortable to wear, or the obvious size constraints that may be apparent. Then obviously establishing wireless communications, but also aspects like powering of the device. This becomes specifically interesting when you're talking about implants. And yeah, obviously looking at the environment and the channel where the device or technology is employed. And this can be something that changes depending on the patient or the usage scenario. So it means that you need to develop some quite challenging or robust systems. Then obviously safety is paramount when healthcare is of play, and it's very important that no harm is caused to the patient. And something that is becoming more and more of an issue is the spectrum that is available for communication, which is obviously becoming more and more overloaded. So before we get started, for those of you that may not be familiar with FEKO, FEKO is a state-of-the-art simulation tool for electromagnetics, and the focus is on modeling of scattering, radiation, and waveguide problems. We specialize in a broad range of applications, varying from standard antenna design and antenna arrays through antenna placement, microwave devices, EMC, and also obviously bioelectromagnetics. Now, one of our major focuses at FEKO is at the development of different numerical technologies or methods for solving these electromagnetic problems. So we have a range of different methods that are available, and have gone even further to introduce the hybridization of these different solvers. Now, in some cases, by using hybridization approaches, you can provide sort of a best of both worlds solution, whereby you are able to overcome some of the limitations with one method by coupling it to another method that may have advantages in that range. And that's kind of the philosophy that we have here, and the approach is to make all of these solvers available under a single license. So I hope we have prepared an interesting agenda for our talk today, and we're going to look at several different aspects today. Initially, we're just going to start off looking at some different anatomical phantom models that are available, and obviously this is a key area in many healthcare or bio-EM simulations. So we're just going to review what is available for FEKO. Then we're going to look at two different case studies for MRI, the first being a 7 Tesla head coil design, and the second being a 3 Tesla spinal array. And in conclusion, we will finish looking at a range of different implant devices, where we are focusing a bit on the antenna design and safety aspects. So that's the agenda for the day. And I think especially for the case studies, we want to look at sort of a somewhat numerical focus on there to maybe highlight different approaches that can be applied when solving these kind of problems. Obviously there are always different approaches, so we will try to concentrate on certain strengths in that area. Okay, so to start off, let's have a look at some interesting anatomical phantom examples. Fairly recently, we have started a partnership with a company called Simpleware that is based in the United Kingdom, and they have a broad range of technologies, but part of this involves the development of anatomical phantoms. And here you can see two different models that we have acquired through them. The first is obviously a full body phantom with 12 different tissues, and the second is a detailed head phantom including fairly detailed description of the brain. Now these models are made available through a very high quality tetrahedral meshes, which can be then used directly in FEKO using the method of moment and finite element solutions, so the hybridization solver. And furthermore, these phantoms can be remeshed directly in FEKO, again to be used with our new FDTD solver. So yeah, this is quite exciting news, and for more information and about SimpleWare has the capability then, based on a statistical database of different patients where they have acquired measurement data, they have the possibility to perform scaling in both body mass index or BMI and also in age to cover basically the whole sort of human population. And they do that by basically sampling the statistical model that they have, and then they can interpolate to different stages. So here you can see, for example, the male phantom for different BMI, and just an overview then of the tissue distributions for those different phantoms. And yeah, here you can see a bit more detail, again showing the BMI percentile for both male and female phantoms, and also a boy of 1 year old. So starting off with the skeleton, and here you can see then the addition of some tissues, and finally the skin layers. So this is quite useful because it allows you to address then a very broad range of different subjects to for example, address those issues that we spoke about before of robust design. Another area where they are very strong is also the provision of detailed phantoms, so detailed tissues. They have very high resolution images available, for example, for the lungs, or here you can see some brain tissue, and also showing veins and arteries in the hand and the feet. So those were the models that are available through SimpleWare. In addition, FEKO does have a range of different phantoms available directly, which can be downloaded by customers through our website, and these range from fairly simple homogeneous phantoms through to more complex tetrahedral mesh models from whole body and different head phantoms. Okay, so at this point we are ready to start our first case study, but before we do that, we would just like to launch our second poll, which I've just begun, and yeah, could you please go ahead and vote for that? The question is, which solver do we believe is the most suitable method for addressing bioelectromagnetics? Okay, thank you very much. Okay, so the first case study we would like to look at today is focused on a 7 Tesla head coil design, which was based on a publication by Dr. Wang. Obviously, some of the challenges involved at designing systems at 7 Tesla is addressing homogeneity over a broad region of interest. And yeah, so we're going to start off looking at the initial design of the system This is a simple IQ feed birdcage coil, and here you can see the geometry that has been modeled in FEKO. We're using 16 rungs for the system, and you can see basically the two feed channels placed in the rungs and the tuning caps which are distributed through the system on either rung end, and finally the RF shield there. And what we'd like to illustrate here in this case study today is obviously look initially at some of the standard performance parameters for MRI, like assessing the resonance of the system, the B1 plus field, and homogeneity, and efficiency of the system, and so on. And in addition to that, we're going to look at some of the computational requirements for these kind of simulations. Okay, so when you design a system like this, one of the first things that you may be interested in is to ensure that you have, in fact, excited the correct resonant mode for the system. So using the tuning capacitors, we can shift the resonance frequency for the system, and we can look obviously at the S parameters for the system to see that we do indeed have a 50 ohm or near 50 ohm system, but still it could be possible that we are actually exciting not the fundamental IQ or quadrature mode for the system. So here you can see some different ways of interpreting the actual resonance for the system. So obviously near resonance for the empty birdcage coil, we would expect to see a homogeneous field distribution, which can nicely be seen here. This is the magnetic field at the center of the coil. Another way to visualize the resonance is then also looking at the polarization of the field. And here we are just showing basically the animation of the vector field view, again at the center of the coil. So we're basically changing the phase of the field, and you can nicely see that the rotational component of the magnetic field as we expect here. And finally, another trick is that we can look at the phase distribution. This is no longer at the center of the coil, but passing through the end rungs or the capacitors. And basically we have a strong coupling of the current that is flowing here in the end rungs to the Z component of the magnetic field. And we can basically expect then sort of a linear phase distribution throughout the field in this plane. Then in addition, we would like to look obviously at the B1 plus field or the B1 minus field. And here you can see the B1 plus field and polarization efficiency, which is calculated by the ratio of B1 plus over B1 minus, in both cases at the center of the coil. So here we're still looking at the empty coil, so things are quite straightforward as we expect. In the next step, we introduce an anatomical, a homogeneous head phantom, and we start to use this as a load for the coil to assess the field distribution in the region of interest. And what we see obviously now is by introducing the load that the field is no longer quite as homogeneous as we had seen before. And we can also look at this, here I'm showing a sort of 2D plot across the region of interest, and that's at 4 different slices in the region of interest. So what we see then is the homogeneity now is about 30 to 50% from the peak in the center down to the trough there. So this is, I think, quite standard for initial design. And in the paper by Dr. Wang, he proposes a an approach whereby he uses elliptical elements, sort of parasitic array, to improve the homogeneity in the head. So he introduces these elements to improve the homogeneity in the region of interest. In addition, here you can just see the SAR distribution. This is the unaveraged SAR, but we can also calculate the average SAR, spatial peak average SAR, to ensure that the system is within the limits. And in the final step then, using the model, the head model that I showed before from Simpleware, we evaluate the B1 field again under realistic loaded conditions. So here you can really assess, well, what sort of B1 field magnitudes am I able to achieve in specific tissues, for example, or certain regions or subregions there. Now, just some general comments, firstly about electromagnetic simulation here and kind of the approach that we followed. Initially, we have chosen method of moments to simulate the empty coil, and method of moments is quite suitable in this case because of several reasons. Firstly, it resolves the curvature of the round coil very well using the triangular mesh, and obviously inherently captures the actual currents that are flowing on the system very accurately. That's quite fundamental to method of moments. Secondly, it is also quite attractive from a computational point of view. The simulation of the empty coil can be run in less than a minute and uses a negligible amount of RAM. Things get a little bit more interesting when we introduce the homogeneous head phantom. It becomes less clear whether to choose method of moments or hybridized with finite element or FDTD. In this case, we have used method of moments again, and we still have a very quick simulation time of about 12 minutes. And also the RAM has increased a bit. So maybe, for example, FDTD would be more efficient from a RAM point of view, but the simulation time might be similar. In the final stage, it gets a bit more complex, where we show here the behavior for the anatomical model using method of moments hybridized with FEM. So the actual volume coil is still simulated using method of moments, which is then coupled to the finite element region, which is literally just made up of the tissues for the head. So we have the triangles for the system here, and then the tetrahedral elements for the finite element. And in this case, we used a pretty fine resolution. So I think the average size was about 6.3 millimeters for the tissues, and in some cases, obviously, where there was detail, we had more elements. So we can see now the simulation time is still acceptable, but we have quite an increase in RAM. So depending on our choice here, we could also maybe use FDTD in this range. But I think what is most interesting here is that, especially for the empty coil and possibly also with the homogeneous phantom, is that we can certainly still consider using or applying optimization strategies because the individual simulation time is very low. So we could follow an approach whereby we can easily look at using our genetic algorithm-based optimization, for example, either to try improve the field homogeneity or improve the field deposition in other regions, for example. So these simulations were run just on a Lenovo laptop. And of course, you can also use a more powerful computer to improve the simulation time. Okay, the second case study that we would like to look at today is a spinal array design at 3 Tesla. And the design requirements here were to develop a 7-element surface array, which you can see over here, for spinal imaging at 3 Tesla. And we wanted to use an element size of approximately 130 by 150 millimeter and try to cover an area of about this size for the system. And obviously we wanted to look at to achieve that the array is tuned and matched at 124 megahertz. We plan to do this using distributed capacitors through each loop, and also introducing a matching network for each individual loop. And the design goal then was to achieve a S11 or S parameters below minus 15 dB, and for coupling we wanted to achieve minus 10 dB between neighbors. Okay, so we started off with the single loop design, just to illustrate again what we've said before. So we have a feeding port with the matching network, and then we introduce the 5 capacitors for tuning the system. And yeah, the goal is also to obviously to have a nice homogeneous field, like you can see here, around the loop. And this is obviously improved using the distributed capacitor system. Okay, so here again we have an interesting approach to deal with the optimization. So obviously it's a somewhat complex system to optimize, and one attractive approach to follow here is to introduce basically a homogeneous half space using a muscle like tissue. And using this approach, obviously that needs to be simulated with method of moments then. We can basically emulate the proximity of the human body to the array. In other words, the array sees at least a semi-realistic body load, and we can do this without actually increasing the computational requirements in any way. So this may mean that we are able to run an automated optimization over the whole system to achieve the S-parameter design goals. So we start off with, as before, we said we do an initial design just for the individual loop to ensure that the parameters are within range. And yeah, this is actually in the next stage. So the individual loop can be simulated in basically less than a minute. This is a very straightforward problem for method of moments to solve, and obviously there are not too many triangles in the geometry. From here we can basically populate the sort of the initial idea for the array, which you can see here, and we then feed this into our optimization system. We use initially an orthogonal spacing of 2 millimeters between the elements, so they stack up vertically. And yeah, basically we look at the lateral positions for the 4 elements in this area, meaning that we move them in y plus and y minus and x plus and x minus around there, and also then the spacing of the outer elements. So basically we pass all of these variables to the optimization, and obviously now, so an individual element simulates in about a minute, but now we have added 7, so we can expect the simulation time to be slightly larger, but still well within what can be used for an automated optimization. And we see then that the optimization takes, in this case, less than 2 hours. It was about 2 hours. and converges in 39 iterations. And at that point, once we have obtained the best design, we use, that was that last point in this slide, a tool, a third-party software tool called OpteniLab, which is a tool for automated matching network design. And one of the very attractive features here is that the tool also allows us to do multi-port matching. So we can do a simultaneous multi-channel matching for our array. And here you can see then the S parameter results, where we want it to be under 10 dB, minus 10 dB for the coupling, and minus 15 dB for the individual ports. And here what we are showing is the initial spacing and how the optimizer has now generated the optimal geometry for the array. So remembering now, of course, this was done as an initial first step using this concept of a homogeneous half space. And obviously then in the next step we may need to do some fine-tuning or tweaking of the design. But what we expect is that using the half space we should be very close to a realistic scenario, and by then adding the anatomical body as we see here, that there should not be a significant change in the performance, and we can tweak the design. So in this case the body phantom was had 13 different tissues. You can see some of the tissues in this image, and also then the quality of the mesh here for the FEM simulation, using an average element size of about 8.3 millimeters, and that results in about 1.3 or 1.4 million tetrahedral. And here we are just showing the I think the B1 field for a excitation there. So let's have a look again at the computational requirements for these simulations. Initially we said the simulation time, okay, so this is for the full array using the dielectric half space, was solved in about 3 minutes and uses about 200 megabytes of RAM. We then run the optimization of the system, and again our RAM is the same because the meshing is not really changing of the system, and as mentioned before, that can be achieved in about 2 hours, less than 2 hours. And in the final stage we include the detailed anatomical model, and this can be solved in just over 2 hours here, so it's at about 2.5 hours. And yeah, where we do see an increase then is in the RAM usage for the FEM element. I think also what is maybe interesting to mention at this point is the system that we have designed here is a planar array, and obviously if you want to move to conformal elements, also introduce elements over the chest depending on the application, this would also be a strong argument to continue using the method of moments, for the same reasons as before, that the triangular meshes will nicely discretize the curvature of the geometry. However, when considering the anatomical phantom, performance could be quite equal between FTTD and the hybrid solution with MOM and FEM. And again here in this case, when we are using the MOM and FEM regions, just for clarity again, what that actually implies is the actual array is still simulated using method of moments, and we then apply finite element, or it's coupled into the finite element discretization of the anatomical tissues here. Okay, so this is bringing us to the last part of the talk. I think at this part we will also just launch our last poll for today. And the question is related to which application you're most interested in from a healthcare point of view. So if you could please go ahead and vote. Okay, thank you very much. Okay, so in closing today, I would just like to show a few different simulations or technologies that are related to implant antenna design or safety. And the first of these is an injectable implant, which is designed for the 2.45 band, that's the ISM band. And obviously, already just by the name, if you think of an injectable implant that has clearly some very strict geometrical constraints, and here you can see the diameter of the implant has to be less than or basically a millimeter in size to allow it to be injected, and also obviously the length cannot be too long. So here it's about 2 centimeters in length. So already just from the size constraints, the design lends itself quite intuitively to a high frequency design. Otherwise it would be very challenging to design an antenna at lower frequencies to work in the system. So it's quite a novel technology, and the idea of having an implant which does not require surgery and can be injected very easily into the patient is obviously very attractive. And I think there is basically some biosensors also included in the design which will then record certain vital signs. And yeah, the antenna design that is chosen here is this sort of dual folded dipole design. So it's basically folded like a helix, and also the end between the two folds are shorted. And basically the link budget that is required for short-range communication that's less than 20 meters is greater than -7 dB. And what we do here is we use a multi-layer phantom for the simulation. Because of the high frequency, we have a very localized field behavior, and it may not be necessary to include a full body model or more anatomical detail, because the field is very localized in the tissue, very high losses at those frequencies, and obviously the wavelength is much smaller. So here what we are showing is the phantom is made up of 3 different tissues. That's a muscle layer, a fat layer, and the skin layer. And obviously the antenna is implanted at the boundary between the skin and the muscle. And here we're showing then the field distribution in the tissue, and also then the far field radiation pattern. And we can see then the peak gain is, in this case, -16.3 dB, so we can basically achieve the short-range communication link budget then. This is another antenna design for a pacemaker application designed to operate in the 400 megahertz ISM band using a low-profile, high-gain PFA design. And yeah, basically here we're showing the surface current on the resonant antenna, also including the casing for the pacemaker, and the link budget was calculated for device telemetry such that it would be possible to achieve communications up to 10 meters, provided a minus 31 dB antenna driving power. Then another very interesting aspect when talking about implants is the compatibility or usage scenario for MR environments, and the issues that are important there is what sort of local SAR do you have in the region of the implant, and obviously also heating that may occur through localized or induced currents that may occur on the implant. So what we're looking at here is a sort of typical compliance scenario for a 3 Tesla MRI Birdcage coil, and we are using an ASTM phantom based on the 2009 standard, which is the rectangular bath phantom. And what is interesting in this case is that if we look at the wavelength in the muscle simulating liquid, it's about 30 centimeters, which is about twice the length of the diagonal length of the implant in this case. So in this case we're looking at a hip implant or a hip replacement. So in other words, we kind of expect a half wavelength resonance that could occur in this scenario. So yeah, basically what we're showing here is the SAR distribution, and quite easily you can see the localized SAR distribution that occurs at the tip of, or either tip of the implant, and this is in fact due to this sort of resonance behavior that strongly couples to the implant. And in this case the spatial peak average SAR was calculated to be less than 1 watt per kilogram for 0.5 microtesla at the center of the phantom. Then also of interest is we have recently developed a script for calculating the temperature increase. So it basically solves the bioheat or the Pennett's bioheat equation, and we can use this then to calculate the temperature increase. In this case we're showing a scenario where the MRI system is active for 600 seconds, so 10 minutes, and we are looking at the temperature increase in the close vicinity to the tip of the implant. So it's around about just less than a degree. And also we can visualize the temperature increase. So this system is for a 64 megahertz or 1.5 Tesla Birdcage coil. And here we're showing the SAR distribution for the implant and the temperature distribution after 10 minutes. And just before we get to the conclusions, to wrap up, if you are interested in using the temperature script, you can find the script available for download under our Lua scripting section in the website. There are also some examples included illustrating how it can be used, so please do go ahead and download that for usage. So just to conclude our talk today before we open up for any questions, as we said before, I think there is a fascinating time at the moment, or time period, for the healthcare industry in terms of the technology that is being developed, and there seems to be a very strong correlation between this technology development and basically the wireless technology industry in general. So they seem to grow hand in hand, and the future really looks very attractive in terms of healthcare and the new systems that are being developed. At the same time, FEKO has a proven record for accurate simulation and design for antennas, and is prevalent in the healthcare industry to basically support this technology surge in a role to try to design and improve the products that are available and ultimately lead to better products for the industry. So at this point, I would like to thank you all for your attention today. I will have a look now to see if there are any questions. Please also feel free to either send questions through now using the webinar window, or alternatively you are more than welcome to send us an email after the WebEx to webinars@emss.co.za, and we will get back to you. And finally, as Fiona mentioned, there will also be a recording of this webinar available later, which you can download. Okay, so I see there are a few questions here. The first question is related to the thermal script, and the question is the thermal script generalized, or is it specific for this example? Now, that's quite a relevant question. For those of you that are not familiar with the application macros in FEKO, we are able to build, using the Lua scripting interface, we are able to build actual user interfaces from the Lua environment. And currently, right now, we have actually just completed doing that for the thermal script. So the answer to that question is, at the moment, the script that is available on the website is specific to that example. So there are some material parameters, for example, that have been written into the script directly. However, in the next few days, if you go back to the website, let's say maybe in 1 week, early next week, we will be able to provide a generalized version of that script, which will allow you to work on any simulations that you have. The dialog will open, asking you to assign initial parameters, including time step and how long you want to evaluate the simulation for, and also do the material assignment in a dynamic way. There was also a question regarding the general examples for MRI, and specific to the surface coil array example that I showed. We do have some examples available through the website in terms of the I think some of them are hosted for download through the white papers. We have also added a tutorial or example guide example for a head coil with an elliptical phantom, And alternatively, for the surface coil arrays, we don't have anything online at the moment, but we can make those available. There was another question related to the thermal script, and the question was, would it be possible to use the thermal script to introduce field results that were not calculated with the FEKO? And the answer would be definitely yes. The way the script is written at the moment just works directly with the data field, obviously using the SAR field distribution in a specific near field request, but it would be quite straightforward to replace that with a field distribution that could have been calculated analytically, for example, or in any other way, and then that would still continue to work. Okay, so that seems to be all the questions. So I would like to thank you all once again for your attention today, and again invite you, if you do still have further questions, please feel free to contact us directly, and we will be happy to get back to you. Thank you very much.